Thank you very much for the introduction. Thank you very much for inviting me here. It's a great pleasure and a great honor to give this lecture here in the Kavli session. We're all familiar with the saying, a picture is worth 1,000 words, or seeing is believing. And that not only applies to our daily life, it definitely applies also to the sciences, because it's probably not a coincidence that the beginning of the natural sciences in history very much coincides with the invention of the light microscope. Because with the light microscope, mankind was able to see for the first time that every living being consists of cells as basic units of structure and function. And of course, with light microscopy, bacteria were discovered as causes of diseases. However, we also learn at school that the resolution of a light microscope is fundamentally limited by diffraction to about half the wavelengths of light. And if you want to see smaller things, such as viruses, we have to resort to electron microscopy. Now, there's no doubt about the fact that electron microscopy has achieved a much higher spatial resolution. In a number of cases, you can have a resolution that goes down to the size of an atom. So the question comes up, why do we still care for the light microscope now that we have the electron microscope? The answer to that question is given in the next slide, where I made a little experiment. I tried to find out how popular the light microscope is. And therefore, I took this basic medicine journal publishing studies in basic advancements in medicine, and I counted the number of studies in which an electron microscope was used and those that used the light microscope. And now you see which of the two won. So light microscopy is still the most popular imaging modality in the basic life sciences. And there are two strong reasons for that. Now, the first reason is that light microscopy is the only way by which you can look into living cells. So if you want to follow up what's going on in a cell non-invasively, there's no alternative to using focused visible light. But there's another reason. As we know, to electron beams or to light, all the different proteins in a cell basically look the same. And if you want to see a certain protein species, we have to highlight that particular molecule that we're interested in. And that's relatively easily possible in a fluorescence light microscope, because in a fluorescence light microscope, what we do is basically we highlight the protein of interest by attaching a fluorescent molecule to it. Now, a fluorescent molecule has, as we all know, a basic energy state, a ground state with some vibrational substate, and a basic electronic excited state. And then if you shine light on it, for example, green light, then the molecule will be able to absorb a photon of suitable energy. Then it will end up in a higher vibrational state of the electronic excited state. And after some vibrational relaxation, it will end up here in this state, which is the actual fluorescent state. And then, after about a nanosecond, the molecule comes down by emitting a fluorescent photon. Now, because of some of the energy is lost here in the vibrational decay, the fluorescent light is redshifted in wavelength, and that makes fluorescence microscopy extremely sensitive. In fact, it is so sensitive that you can detect even a single molecule, as has been discovered by my co-laureate W.E. Myrna. However, if there is a second molecule, a third, a fourth, or a fifth, coming closer together to the first molecule, then about 200 nanometers, as we all know, we cannot tell them apart. So the resolution is of course about telling things apart, discerning details, seeing features as distinct entities. And so you can imagine that because of the resolution barrier, diffraction resolution barrier, and because of the lack of the microscope, or the inability of the microscope to see structural details below this level, a lot of information is lost in the cell. And therefore, it's clear that if you manage to come up with a light microscope or fluorescence microscope that has a much higher spatial resolution that overcomes the diffraction barrier, a lot would be gained in the life sciences, and this would have a tremendous impact in the life sciences. Now, first, we have to understand where this limit comes from. Now, we all know that the most important element, optical element of a microscope is the objective lens. And the role of the objective lens is to concentrate the light on a point, say to focus light onto a point. But because light propagates as a wave, we get here a blob of light, the main diffraction maximum, that is about 200 nanometers at least in the focal plane and about 500 nanometers along the optic axis. And this has a major consequence. If we are having, say, several features, molecules, whatever, falling within this main diffraction maximum, then they will all be flooded at the same time with, say, excitation light or illumination light. And then, of course, they will also produce, say, fluorescent light or backscattered light basically at the same time. And so if you try to collect the backscattered light with a lens and focus it onto a detector, of course, we will have from each feature, of course, a blob of light that is here also diffracted. And each of these features or molecules, of course, will produce light basically at the same time because they're flooded at the same time with this diffracted beam of light. And therefore, what will happen, the signal will overlap at the detector. So as a result, no matter what detector we use in here, the signal here will be confused. It could be a photomultiplier, of course, it could be the eye or even a pixelated camera. The signal that is produced here at the detector from these features, from these molecules, will be confused. And therefore, people believe that you cannot do anything about it. Now, the person who realized this problem early on was this man, Ernst Abbe, who lived at the end of the 19th century. And he coined this diffraction barrier in an equation that is named after him. It's saying that in order to be separable, the features of the same kind have to be further away than the wavelengths divided by twice the numerical aperture of the objective lens. And this equation can be found basically in any textbook, of course, of physics, optics, and also in textbooks of molecular and cell biology, of course. Not only there, you will also find this equation written in stone, basically, in a memorial that was erected in honor of Ernst Abbe. And this is actually what we want to beat. We would like to show that we can discern features that are closer together than the distance of d. Not only this was the theory and the belief, of course, it also was a fact. Until the end of the 20th century, so the best resolving microscope was the confocal microscope. And if, for example, if you want to take a picture from a cytoskeleton or so, this is a fluorescence image, then the best that people could get at that time looked like this. But now, it is like this. So this is now a recording with a super resolving microscope, with a stat microscope, and obviously a transition has happened. Now this transition, of course, has had many consequences, and one of the consequences that it had for me, at least, was that I had the privilege of meeting Scandinavian kings. Now the first one was King Harald of Norway in September last year, and then slightly later, the King of Sweden with a nice diploma and another medal, and followed by a very nice banquet with very good food and very nice company. But I believe you're not interested in the gossip, you're interested in how it works. Well, so I'm going to explain to you how it works. So what actually made the transition here from this diffraction limited, say, image to this high resolution image? Now let's get back to the problem. So I was a student at the late 80s, and I did light microscopy, confocal microscopy in those days. And I started to wonder, how does it come that this diffraction barrier was, say, realized at the end of the 19th century, but then it was 1990. So much physics happened in the 20th century. Quantum mechanics was invented, molecular spectroscopy, and so on. So there's a lot of new physics that came up and that was written in textbooks. There must be at least something that could be used to overcome the diffraction barrier in a light focusing microscope, in a far field light microscope. So at some day I put it down in writing. Why did I write far field? Because at that time there existed already a concept, the so-called near field optical microscope. But a near field optical microscope uses a tiny tip of nano-sized, nanoscale dimensions, and of course overcomes the diffraction barrier by confining the light specimen interaction with this tiny tip. But that didn't look like a light microscope to me, because that's limited, of course, to imaging specimen surfaces, and it resembled very much a scanning tunneling microscope. I wanted to look into the diffraction problem for a light microscope that looks like a light microscope that uses regular objective lenses. And so I started screening textbooks to find a phenomenon that could be used to overcome the diffraction barrier. And one day I opened this textbook. I thought maybe there's something with photon statistics or something in it. And I came across stimulated emission. And all of a sudden I was electrified, because I came across an idea that really changed the game here. Now, why was I so electrified? Let's get back to the problem. We have the objective lens and this diffraction blob here, 200 nanometers wide. And as I said, all the features that fall within that blob of light, of course, will produce simultaneously fluorescence here at the detector. And this is why we cannot discern the features in here. We cannot change the fact that we have a diffracted beam in here, but maybe we can change the fact that all the molecules that are flooded here with light, with excitation light, with illumination light, are capable of scattering light back to the detector. In other words, if we manage to put some of the molecules in here into a state in which they are not capable of producing light at the detector, then we can discern those that can produce light here from those that cannot produce light. So if we manage to keep some of the molecule in a dark state, then we should be able to discern the bright state ones from the dark state ones. So the key, you see, is not the change of the way the light is propagating. The key is the state. Think about the state of the molecule that you look at, and then you can kind of incorporate it in the way the image is formed. Now you ask, we're probably asking now, are there any dark states in a fluorophore, for example, if you do fluorescence microscopy? Well, look at a basic energy diagram. We have the ground state and we have the excited state. Well, it's very clear. In order for the molecule to be bright, to emit light, it has to be in the excited state. If it's in the ground state, it can't. This is a dark state. So the ground state is a dark state. And now you know why I was electrified. Simulated emission does nothing but producing dark state molecules. It instantly gets molecules back down to the ground state, and then, of course, the molecule is in the dark state. And if it's in a dark state, if it's produced here in a dark state, then it cannot send light back to the detector. So that was the basic idea behind what is called now the STED microscope, and I would like to show you how this microscope actually works. So we have here an objective lens, and this is the sample. And of course, we do have light for turning the molecule on, so from the ground state, which is dark, to the bright fluorescent state. Now, this green light that excites molecules is, of course, diffracted here in the focal region to about 200 nanometers. And all the features here, all the molecules that reside within that spot of light, produce simultaneously, more or less, fluorescence here at the detector. And so the resolution in this arrangement will not be better than what is given actually by diffraction. Of course, how do we get an image here? We just scan the beam across the specimen, but again, the resolution will not be better than what is governed here by diffraction. But now let's assume we use a beam of light that turns molecules off by instantly sending them down to the ground state in the case the molecule has ended up here in the excited fluorescent state. And so what do we have to do in order to make simulated emission the predominant phenomenon? Well, we have to have redshifted light because we want to couple this state, to this higher vibrational state, so that the molecule, of course, is not excited by that red-shifted beam of light. And then, of course, we have to have a certain intensity. We have to make sure that there is a red photon at the molecule in the case the molecule gets excited. So in other words, there's a finite probability of interaction, there's a finite cross-section, but if you apply a beam of light that is strong enough, and this is the intensity of the red beam, so that there is always a photon present at the excited molecule, you can be sure that the molecule instantly returns to the ground state as soon as the molecule gets excited. So in other words, so if this is the intensity of the red beam, for a certain intensity, you have turned the ability of the molecule to occupy the excited state off. Because as soon as it gets up, it has a quick vibrational decay, it instantly is pushed down. Here it quickly relaxes, and you're not Rabi-cycling it all the time. It quickly relaxes here to the ground state, and so you basically disallow the molecule to occupy the excited state. You can turn it off. No matter how many green photons you put on the molecule, the presence of the red beam, the red-shifted beam, turns the molecules off. And now, you see what we want to do. We don't want to turn off all molecules. It wouldn't make sense. So we prepare the beam such that it produces a ring, just adding a piece of glass, a phase modulator here, so that it's not focused, the beam is not focused into a spot, but into a ring. And now, of course, we can turn off those molecules if the red beam is bright enough. But here at the center, since this is a donut, there is zero intensity, and so we cannot turn the molecules off in here. Now, let's just assume we want to see just that strand in the middle. So we have to turn these molecules off and those off as well. Of course, we can't make the ring smaller than that because that's limited by diffraction, but we don't have to do that, simply because this is about turning off molecules. So the only thing we have to do is we have to make sure that the red beam is bright enough in order to make sure that here, where it's weaker in percentage, it's in absolute terms beyond the threshold. And so just by making the beam brighter, the region in which the molecule is allowed to occupy the excited state becomes smaller, and only those molecules here are allowed to emit because those are not allowed to occupy the excited state. And now you see how we get the image. We just scan the beam across the specimen, and now we can separate this fiber from that fiber simply because the molecules are forced to emit time sequentially because we play this on-off game with those molecules. Okay, now we can instantly agree on the fact that what we do in here is saturate. You can think about this as a nonlinear phenomenon that we use in here. But I'm warning you a bit. This is not a good line of thinking. The nonlinearity is not a good way of thinking. What actually happens is we prepare the molecules in two different states. And in order to make that clear, I'm removing here the donut. So here, all the molecules are flooded with green lights, but only here in this part, in the center, they are allowed to assume the on state. Here, at the outer part of this green area, they are forced to stay in the ground state, and that's the point. So here, they are forced to stay in the ground state, whereas only in here they're allowed to occupy the on state. And because they are now in two different states, despite the fact that all of them are flooded with the same diffraction beam of light, we can tell them apart. And this is how we separate features in here, because we get them, say, sequentially in two different states within the zone of diffraction. Okay, I'm putting the donut back. And this concept turned out to work. This is a standard, say, resolution of something that you cannot see what it really is. And now we turn on this stat beam, and as a result, we have a much higher spatial resolution. We can see these are nuclear pore complexes. The resolution is here in the red channel, improved by an order of magnitude. And now you can zoom in and see the details. So this nuclear pore complex has an 8-fold molecular symmetry. These are subunits here, molecular subunits. If you make the comparison with the standard resolution, well, there's no comparison. And here you have, of course, a much higher gain in information because of the higher spatial resolution. Now, if you get a much higher spatial resolution, you can learn something that you didn't know before. And so we teamed up here with a group interested in HIV, so in viruses, biology. And so the question here was, this is an application of the method. The question was how a certain protein called ENF is distributed on HIV particles. Now, HIV particles have a diameter about 140 nanometers, so it's substantially below the diffraction barrier. And if you want to see nano-sized details on them, of course, the resolution has to be much higher than that. Now, in the normal case, you don't see how this protein ENF is distributed on the HIV particle. But now, if you take the stat image, you see that it forms patterns. And what has been found out, actually, in this study is that mature particles, so the mature HIV, has all its ENF proteins here in a single place. That's obviously required in order to infect the next cell. So you can get, say, basic insights, mechanistic insights about, say, HIV infectivity and how HIV works. So this is one example. Of course, a strength of focusing light microscopy, far-field light microscopy, is that you can image dynamics. And this is just a confocal, so a high normal resolution snapshot, and this is now a stat recording done in quick succession, so 28 frames per second. This is a video of synaptic vesicles in an axon of a living hippocampal neuron. So it shows how these vesicles, these are little containers about 30 to 40 nanometers in diameter, move about, and you can learn something about the trajectory and their fate and so on. Now, live cell imaging at the extreme is to go straight to a living system. And in this particular case, we opened the skull of a mouse. This was a transgenic mouse, and some of the cells, the neuronal cells in the brain of this mouse, express the fluorescent protein. And now, because we have a higher resolution, we can quite nicely see actually the so-called dendritic spines here, these little morphological features here in the brain of the mouse. And not only you can see them with high resolution, you can also follow their dynamics. Because this is, as I said, a light focusing microscope where you focus into the brain of the living mouse. This is about 20 microns deep in the brain of the living mouse, and it's actually worthwhile zooming in here and see these little morphological changes. This was discovered because of the high resolution. And so my message here is that not only we can see such features, but I firmly believe that these methods will be refined, and at some point we will be able to see the protein distribution right at the synapse of a living system, perhaps give visual cues to the mouse, and then really see what's going on the level of a synapse in terms of how the protein are distributed and how they change in time. Now, this is just to show you that you can get three-dimensional images. You can focus into the brain tissue in this case and get a three-dimensional, say, rendition of the data that is produced, because it is a far-field optical method. Now, with that, I'm coming back to the resolution. So the basic question, what is the spatial resolution limit that we have now in this concept? Well, I think the answer is relatively easy to give. The resolution will be, in the end, be determined by the spatial extent in which, say, the emitter or the molecule is allowed to assume the on state. And so it's clear that if we increase the power of the red beam here, more molecules will be shut off, so more molecules will be disallowed to occupy the on state, and so the region D will become smaller. And in essence, the resolution will be determined by the power that is applied onto the maximum of the donut here at the donut crest, and the threshold intensity, which is the intensity that is required to make the transition, say, on to off certain, more or less. So to be sure that it's in the other state. And so this ratio, if you do the mathematics or if you measure it, you will find here in the denominator, it scales with the square root of I over IS. And so this is obviously now governing the spatial resolution. And clearly, if this ratio becomes large, like 5, 10, 100, and so on, D will go down to 0. And so the question comes up, so what is the conceptual limit of resolution? I mean, 0 is kind of meaningless in a way, at least to some extent. Now, let's play a little game. So in here, the resolution is given by the spatial extent of the two molecules in here. So we cannot discern the spatial resolution. We cannot discern the two molecules simply because the resolution is not enough. The molecules here are allowed to emit simultaneously. But now, if you increase the intensity a bit, then only one molecule fits into that area in which the molecule is allowed to assume the on state. And now we can separate this molecule from the neighboring molecule simply because when one of them is off, the other one is on, and vice versa. So we play the on-off game on the level of a single molecule. Of course, if all the molecules here are dark, they're totally dark, one photon is absolutely enough to identify the molecule in here because the position of that molecule here is firmly determined by the photons that fall on the sample, by the red photons. So in other words, the conceptual limit here is indeed the size of the molecule. So the new resolution limit, if you like, is the size of the molecule. This is not surprising because after all, we separate by having molecules in two different states. So the molecule is the smallest separable unity, if you will. Now, this may sound like a proof of principle or a kind of a conceptual game that I'm playing in here. So the question is, can you come up with an experimental demonstration that you can get down to these values? Now, in practice, with organic molecules, you get a spatial resolution with this concept that is of the order of about 20 to 30 nanometers. And so one has to refine, of course, the molecular states and so on to get to a higher spatial resolution. And with organic molecules, that may work in the end, but right now, the resolution is, as I said, of the order of 20 nanometers. But there are, of course, emitters, fluorescent emitters, that are almost ideal, that you can turn off as many times as you want. They do not photobleach, they do not disintegrate. And these are, for example, fluorescent color centers in solids, like the charged nitrogen vacancy color centers in diamonds. And with those, of course, we demonstrated a very high spatial resolution. You can turn them on and off, as I said, as many times as you want. There's no photo degradation. And so you can squeeze the area in which the molecule or which the emitter is allowed to assume the on state down to the single-digit regime. Now, this not only is a proof of principle experiment that you can get down to these values, it may also have practical meaning because, as you may know, these charged nitrogen vacancies are hot candidates as qubits for quantum computation or as for magnetic sense. And this has been actually pioneered by Jörg Wachtrup in Stuttgart, Von Walsworth, and Michel Lukin at Harvard. And maybe that is a very good way of reading out the qubits or reading out the magnetic fields using charged nitrogen vacancies as sensors. Now, with that, I'm coming back to a generalization of the whole idea. As I explained, the name of the game here is to play on-off, to make sure that not all the emitters that are flooded with the excitation light are capable of sending light back to the detector. Now, stimulated emission is probably the most fundamental way of turning a molecular emitter off because it sends the molecule from the fluorescent state back down to the basic ground state. But definitely it's not the only one. It's not the only way to play on and off with a fluorophore. So when I realized that, this concept of stimulated emission, depletion stat, I thought, okay, there must also be other transitions, like the transition to a long-lived dark state. So in this case, this is the off state, and the singlet system is, if you will, the on state, or you can have an on-off transition by a cis-trans isomerization. And you will ask now this is a very basic one, so you find this in any fluorophore. Any fluorophore has a ground state and excited state. Why bothering about those states, like a dark, long-lived dark state or cis-trans isomerization? I mean, cis-trans isomerization is found only in very special fluorophores. Well, the answer is very obvious. Keep in mind, the states that are involved here, the on and the off states, have different lifetimes. So this has a very short lifetime, the on state here. So in a nanosecond, the molecule relaxes. But here, the states involved have a much longer lifetime. Here in cis-trans, there can be a millisecond in cis and a millisecond in trans, or even longer, even seconds. So the lifetime of the states here is different, and here the lifetime is much longer. Now, why is this important? Well, I think it's very obvious, because we play the on-off game in order to separate features, and in order to separate molecules. Now, if you have something that has a very short lifetime, then you have to hurry up creating this difference in states, and you have to hurry up reading them out. So in other words, this difference in states that we critically need to separate features disappears here after a nanosecond. After a nanosecond, you have all the molecules in the ground state. So the difference in states is, of course, harder to keep up because it decays very quickly. But if the lifetime of the states involved is very long, you can say on, off, on, off. There's a lot of time. And so it's much easier to set up. In other words, what happens actually, because if you go to a long-lived states or longer-lived states, the photons that you need in order to set up this difference in states and read them out per unit time goes down. Or in other words, the intensity that is required in order to overcome the diffraction barrier goes down, because that one scales inversely with the lifetime of the evolved states. The longer the lifetime, the lower the threshold intensity here. And so this is why this, say, cis-trans isomerization, and to some extent also these long-lived state transitions are very, very attractive. And so the intensity threshold goes down here from megawatt per square centimeters to kilowatt per square centimeter, down to watt per square centimeters, which you can get with an LED in principle. And so this is, of course, very, very attractive because it decreases the threshold IS, and of course also decreases the intensity I that is required to overcome the diffraction barrier. And let's assume now we take this transition, which is of course very favorable because you can find them also in switchable fluorescent proteins. And so when I realized this, I was very, very excited. And actually, the first switch of GFP was done by my co-laureate, W. Myrna. And we used special fluorescent proteins in this particular example that I'm showing you here in order to demonstrate the use and the usefulness of switching fluorescent proteins. As I said, if you use switchable fluorescent proteins like this, you have a low intensity requirement, so you can easily spread out the light over a large field of view. So this is done actually in here. So we not use just a single donut, use many donuts because it needs so little light in order to do that. And so we spread it out the light to produce many, many, many donuts. As long as they're further apart than the diffraction barrier, no problem. You can image them on a CCD camera, and then just scan the whole thing like this with a few steps. You've taken the image. And so here it was taken actually with more than 100,000 donuts in 2 seconds with low light levels in living cells. So it shows that you can parallelize the whole thing. Not only that, the transition is the decisive thing. The selection of the molecular transition, state transition, is actually absolutely critical. That determines the parameters of image formation. So what does it take to get the best resolution? Now, let's assume you had asked this question in the 20th century. The answer would have been, of course, good lenses. Of course, good lenses. Why? Because the separation of features was done by the phenomenon of focusing. And the better the focus is in here, or the better the focus is in here, the better you can separate. But using focusing for separation is, of course, limited by diffraction. That is very clear. So if we're having several features here falling within this spot of light, then we cannot tell the features apart. So what was the solution to the problem? The solution was not to separate by focusing, but by separate by placing the molecules that you look at transiently in 2 different states for the time point of detection. And so here the molecule is in the on state, here's the off state, and this is why I can separate this from that, despite the fact that they are falling within the same diffraction zone. And I've shown you a selection of states that you can use in order to do that. Now, so what we did is actually we used the beam of light to prepare the position of the state. Here the molecule is on and here it is off. So in this concept, what happened is we controlled the on state with a pattern of light that falls on the sample. So we use a bright pattern of light that determines actually the position on the on state very clearly, and this is just used to detect the fluorescence that is, or the signal that is produced here from the molecule. So how does this compare with the other seminal concept, the palm concept, which was demonstrated first by Eric Betzig and Harald Hess, based on the discovery of W.E. Myrna, that you can detect single molecules? Well, in this case, the on-off state difference is done on a single molecule basis, just one molecule within the diffraction zone. So this is off and this is on, and then it's turned off and on again, molecule by molecule. But since this is done here purely stochastically, we have no clue where the molecule is located. And this is sorted out here by using on states that produce many photons in a bunch. So if you have many photons in a row emitted from the same molecule, you can have a pattern of light here. And the centroid of this pattern of light gives you the coordinate. Then you know exactly where the molecule was located. And so this is the difference between these two concepts. So the precision with which you can find out the position of the molecule is determined by the brightness of this emitter, so by the number of photons. And here, you always need many photons to determine a position, just as you need a bright spot here to determine the position of the on state. It's very clear because one photon goes somewhere within the diffraction zone. With one photon, you can never define or find out a position of a molecule or so. You need many photons in order to find out the position. And so you need many photons either here or there in order to be able to handle the position. But of course, here you need only one photon to detect it. Here you need many photons. Here you need one switching cycle. Here you need many switching cycles. But in the end, and that's the point, the separation of the features is done by an on-off transition. So that's the decisive thing. So there is a common basis of all these super resolution concepts, which is a state transition between an on and off state, which is done for the super separation. And that is now a case fluorescence and non-fluorescent, because this is super resolution fluorescence microscopy. And because this is about two states, I mean, it's clear that the state and the molecules are here decisive. So in the 20th century, it was the lenses that really mattered. And so the resolution was determined by the lenses. But today, it's actually the molecules, because we use the molecular states that in order to have, we use the molecular states for making a separation. That's the key, and that's, of course, strongly determined by the chemistry that we use. So to be more general, on and off is, of course, just an example of two separable states, A and B. And so you can extend this concept just by also going to super resolution principle, absorption, scattering, spin, or whatever microscopy. So the decisive difference is the fact that you separate by states and not by the phenomenon of focusing. With that, I'm acknowledging the people who have contributed to this development, and I'm coming to my final slide. Of course, this equation doesn't describe the situation anymore. We can easily deal with it. I mean, we just put in the square root factor, which means that now it goes down to 0, meaning that's basically the size of a molecule. And now this accounts for the fact that we have this gain in spatial resolution. And if you ask me now, why can we separate this fiber from that fiber, but there's no way of doing that here? Well, it's very simple. At the time those molecules were in the on state, the molecules of that fiber were in the off state, and vice versa. So in essence, it's a very, very simple solution to a long-standing problem. Thank you very much.
We have time for 1 or 2 questions for Dr. Hell. Let's see. Yes, use the microphone, please.
It was a beautiful presentation. I was wondering, it seems that in the second part of your talk, the fluorescence of a single molecule was an important attribute.
Absolutely.
And I was wondering if you could remind us, who do we owe this discovery to, the possibility that one can look at the fluorescence of a single molecule?
I didn't get a question.
Well, the fluorescence of a single molecule is very important. The second
so
part.
W.E. Myrna is going to give the talk right after me, and he will explain that.
Okay, I thought it was Michel Orit.
The first detection of single molecules, to my best of knowledge, was done by W.E. Myrna in absorption. Michel Orit used fluorescence in order to see single molecules by the fluorescence, to my knowledge.
Okay, so this first detection of single molecule by fluorescence.
Yeah, that's
Michel
right.
Orit. Thank you.
One more?
What limits the spatial resolution in the Z direction in STAD microscopy? You showed the mechanism for limiting the spatial resolution in the transverse direction, but how about in the axial direction?
Yeah, so it depends on the way you focus the light. So you can squeeze the area in which the onset is allowed also in the Z direction. In fact, the first experiments did that. Then we later on moved to X and Y. And so the best way of doing that, the highest resolution you get by using two objective lenses, so opposing lenses, that produce a kind of focal interference pattern in the Z direction. So I called it at some point a 4-pi microscope. In fact, Harold Hess is going to talk about such schemes. And in that case, you get down to, if you do it very well, to the 20 nanometer or even 10 nanometer resolution in the Z direction. If you use just a single lens, right now, if you ask me for STAD, it's about 60 nanometers or so. With a single molecule on-off type of methods, I think it's slightly better. You can get down, to my knowledge, to about 30 nanometers or 40 nanometers, depending on the fluorophore. So it's very important to realize here the limitations of the resolution are, of course, given by the molecules, by the states of the fluorophore. It's not so much the way you focus and the lens. So this is really critical. So there is no, say, specific resolution that you get for a certain method, because it depends on the molecules. In the end, the development of the molecules determines the resolution that you get today and in 2 years or in 4 years or 5 years. But the conceptual limit is the size of the molecule.
Okay. Let's thank Dr. Heller once more.